All right, if you're new to digital electronics, think of this as your first day crash course. We're going to pull back the curtain on those tiny, brilliant little components that power, well, pretty much everything. Integrated circuits. Let's get right into it.
Just think about your phone for a second, or your laptop. It's kind of mind-boggling, doesn't it? Inside that device are thousands, maybe even millions, of components, all working together perfectly. It really is a universe of microscopic complexity. And if you're a new designer, just figuring out where to start can feel, well, completely overwhelming.
So imagine you're that engineer. You've got a problem to solve, a specific function you need to create. You have to pick the right building blocks out of a catalog that seems absolutely endless. How do you choose? How do you even start to make sense of what's out there?
Well, you start by asking the right questions. We're going to walk through the 5 critical ways engineers classify any integrated circuit, and that's all going to lead up to our final step, building a solid framework for making those decisions.
Think of this as your secret decoder ring. Instead of seeing an endless list of part numbers, you're going to start to see a clear system, a way to understand what each component is and where it fits into the grand scheme of your design.
So these are the 5 big areas we're going to explore. We'll look at how a chip is made, what it's supposed to do, how it thinks, what it's actually built from, and finally, just how much complexity is crammed inside that tiny package.
Let's kick things off with the first and maybe the most fundamental choice an engineer has to make. Do I use something that someone else has already made, or do I need to build something brand new from scratch?
So on one hand, you have standard products. The best way to think of these is like a high-quality, pre-made toolkit you buy right off the shelf at the hardware store. It's got all the general tools you might need. On the other hand, you have something called an ASIC. That stands for Application-Specific Integrated Circuit. This is like forging a completely custom wrench that's designed to fit one unique bolt and absolutely nothing else.
And here's the big trade-off. That custom-forged wrench, the ASIC, is the absolute perfect tool for that one specific job. No question. But designing it, building it, and testing it is incredibly expensive and takes a ton of time. And that's exactly why, for most projects, engineers rely on those off-the-shelf, standard product toolkits. Okay, so let's say we've decided to go with a standard chip. Our next question is, what's its job? What was this thing actually designed to do? Is its purpose totally fixed, or is it more of a flexible component that we can shape ourselves? Functionality basically falls into 3 main buckets. First, you've got fixed functionality chips. These are like a simple can opener. They do one thing, they do it perfectly, and that is it. Second, you have processors. Think of these as a high-end food processor. You can change the recipe, which is a software, to make them do all sorts of different things. And finally, you have PLDs or programmable logic devices. The best analogy for these? A big box of Lego Technic pieces. They give you all the fundamental building blocks you need to construct almost any digital circuit you can dream up. Now, within this world of functionality, memory is a special case, but it's absolutely vital. ROM, or read-only memory, is like a printed cookbook. The recipes, your software code, are permanently baked in, even if the power goes out. RAM, or random access memory, is more like your kitchen countertop. It's your active workspace. You can read it, you can write on it, you can erase things, but as soon as you turn the power off, that counter gets wiped completely clean.
All right, now we're going to peel back another layer. We've talked about what a chip does, but how does it do it? This really comes down to 2 things: the kind of logic it uses to make decisions and the physical technology it's actually built from. First up is combinational logic. This is pure cause and effect. A simple calculator is the perfect example. The answer you see on the screen depends only on the numbers and the buttons you're pressing right now. It has 0 memory of your last calculation. The output is just an immediate result of the current input. The other type is sequential logic, and this is where memory comes into play. Its next action depends on what state it's in right now. The classic example, a traffic light. To know that it needs to turn red next, it first has to know that it's yellow right now. It remembers its current state, and that memory is what decides its future.
So, what are these logic gates actually made of? Well, they're built using a few different semiconductor families or technologies. You'll hear names thrown around like TTL, ECL, and the one that's most common today, CMOS. You can think of these as different construction materials, kind of like steel, aluminum, or carbon fiber. Each one has its own unique properties when it comes to speed, power, and cost. Now, this is where it gets really interesting, because this slide shows the classic trade-off every single engineer has to face. On one side, you have something like ECL. It's like a drag racer. Unbelievably fast, but it burns through a massive amount of power. You'll find it in things like supercomputers, where speed is everything. But on the other side, you have CMOS. CMOS is like the electric vehicle of the chip world. It's incredibly power efficient, mostly because it only uses significant power when it's actively switching. And that efficiency is exactly why it dominates everything that runs on a battery. This battle between speed and power is one of the most fundamental decisions in all of electronics.
All right, our final piece of the classification puzzle is all about density. In other words, how much stuff, how many of those tiny logic gates can we pack onto a single piece of silicon? And let me tell you, this has changed dramatically over the years.
And this chart just illustrates that evolution perfectly. I mean, we started out with what was called small-scale integration, or SSI, with fewer than 10. That's 10 logic gates on a single chip. And then, as you can see, we just kept going. Medium, large, very large, and now ultra-large scale integration, or ULSI, where we're packing over 100,000 gates onto one chip. This relentless shrinking is the engine behind Moore's Law, and it's the reason the supercomputer of the 70s now fits in your back pocket.
So we've looked through all 5 of our lenses. Now it's time to bring it all home and put it together into a practical framework that any engineer can use to make the right choice for their project.
And here's the crucial point. These aren't just academic categories on a slide. This is your practical checklist. Every single designer answers these 5 core questions, whether they realize it or not. Manufacturing. Do I go custom or off the shelf? Functionality. Is it going to be fixed or programmable? Logic. Does it need memory or not? Technology. What's more important, speed or power? And finally, integration. How much stuff do I need to fit on this chip? Answering these questions turns that giant, confusing sea of components into a map you can actually navigate.
These trade-offs, build versus buy, fixed versus flexible, speed versus power, these are the very pillars of modern digital design. They have literally shaped every single piece of technology we use today. So the real question for the next generation of engineers is what comes next? What new questions and what new trade-offs will define the technology of tomorrow?